And we're recording. Okay, so let's look at the pre-lab. Use available resources to determine the concentration of calcium ions in hard drinking water. What concentrations qualify as hard? So in your little bit of research, what concentrations would you consider to be hard calcium water?
120 to 180 milligrams per liter.
All right, milligrams per liter. All right, cool. Did anybody come up with a part per million?
I said it's 1 milligram in 1 liter.
Okay, so let's go ahead and talk about what part per million means. When you see these things, part per million, part per billion, and there's even part per trillion, what they're referring to is the number of grams of the pollutant to the number of grams of the solvent. So remember, the solute is the thing that gets dissolved in, and the solvent is the stuff that does the dissolving and the solutions together. So a part per million is 1 gram of calcium 2 plus ion to 10 to the 6th grams of H2O. Okay, so that would be a part per million. So 1 gram versus 1 million grams of H2O. And a part per billion would be 1 gram of calcium to 10 to the 9th grams of H2O, and so on. Okay, does that make sense? So in concentrations of water are commonly reported to in parts per million, which is milligram per liter. So this actually is a part per million because this is 10 to the negative 3, and this is 10 to the 3rd. So that is the same as a part per million. So a milligram per liter is 10 to the negative 3 grams, and to 10 to the 3rd, which is a 1 to a million.
So it's just 6 zeros separated then.
Exactly. Yeah. So what you've written up here is 100 part per million to 180 part per million.
Okay. So did you say like it's 1 ppm?
1 ppm would be 1 gram in a million grams of water, or 1 milligram in a liter of water. Oh, this is important. The density of water is 1 gram to 1 milliliter. So that means 1 liter. So 1 liter would have a mass of 1,000 grams. So when you're looking at a milligram in 1,000 grams, that's a part per million. Okay, does that idea make sense? Is a math appearing in your head that you're 10 to the negative 6 or 10 to the 6th away? A milligram is 10 to the negative 3. A liter is 10 to the 3rd. So you are looking at 10 to the 3rd over 10 to the negative 3rd over 10 to the 3rd. That's 10 to the negative 6. So you are looking at a ppm. You're looking at a part per million. So if you said, all right, 0.015 molar, now we have to convert that into part per million. What is the definition of molarity?
Moles over liters.
Moles over liters, exactly. So this is going to be moles over liters. So to get this into ppm, what do we do with the moles per liter?
Find the grams of the moles.
Exactly. So we're going to turn our moles into grams, and then that's going to give us grams per liter, which will be part per 1,000. And if we divide that by another 1,000, we'll get part per million. So we're going to take our 0.015 moles of calcium ion, and every 1 mole of calcium ion, 40 grams, is that right? Is calcium 40? Feels like it's 40. 40, yeah, 40.08. So 40.1 grams of calcium ion. So find out how many grams that is, and then the grams over liters will be part per 1,000, and then we move 3 decimals and we'll get part per million. Use our handy calculation device. So how many grams is 0.015 moles?
0.602.
602? Okay, sorry, 0.602. So this is grams. So the 0.015 molar means we have 0.0. This leading zero thing that I'm trying to adapt to is crazy. I didn't grow up with the leading zero. It's like I wasn't taught that way, so now I'm actually trying to like leading zero. Grams per 1 liter. Okay, so grams per liter is a part per 1,000. So if we want to turn this into a part per million, we're going to have to divide this by 3, and that's going to get us to. So right now we are at, if you will, we are at 0.602 grams, and it's going to be 602 milligrams per liter. Does that make sense, what I just did? So we have grams per liter, which is going to be part per 1,000. 602 milligrams is going to be part per million. Considerably larger than the 120 to 180 that we previously discussed. So we're going to have 602 part per million. All right, does this make sense so far? Okay. So I'm about to erase this. Are we good to erase? Erasing. Okay. So now back to get to the lab. So what's going on in the lab is we're going to titrate. When titrating basically means you put a known or an unknown in a beaker, and then you add chemical to it that reacts. And you have some kind of sensor to tell you when you are done reacting. Sometimes it's a colored indicator. Sometimes it's a precipitate. And in our case, it's going to be a sensor that's going to measure conductivity. So really want you to understand what's actually going on here. So we're going to put in the beaker. We're going to put in the beaker. That's an upside down beaker. We're going to put in the beaker some calcium 2+ compound. And then in the burette, we're going to put some carbonate, CO3 2-. Okay. And then what's going to happen is that, no, actually right here, the calcium is going to react to the carbonate, and it's going to form a cloudy calcium carbonate precipitate. And what we're going to do probably tomorrow, we come back to it 4 days later, is we're going to filter out the precipitate we make. If we tried to filter out our precipitate today, it might work, but we probably just want to allow it a couple days to settle, which is fine. We're overnight usually. Okay, so this is a titration. You have an ion here, and you have an ion there, and you're going to keep adding ion here until this ion is entirely used up. Okay, you keep adding B until A is entirely used up in some fashion. Cool. Now the sensor we're going to use is a conductivity sensor. So the sensor is going to tell us the ion conductivity. Okay. And part of the reason that calcium tastes so gross, a lot of it in our water, part of the reason that unfiltered, unpurified water tastes so gross is because that calcium has a very high conductivity. It's got a +2 charge. And that reacts with our taste buds and like, oh, this tastes weird. It's all icky because of the high charge. So when we start the reaction, when we put in 0 milliliters of titrate, I'm just going to say burette. 0 milliliters from the burette, because that's what this is called, the burette. It's going to have a very high conductivity. And as we add the ions together, what's going to happen to the concentration of that calcium ion?
Gonna go down.
It's going to go down. Why is it going down?
Because the ions aren't floating around the conductivity thingamajig anymore.
Where are they?
They're in a solid form with the CO2 or CO3.
That's exactly right. That is exactly right. And that's what's going on. And that's what the big press for this lab is. As we add precipitate, the conductivity is going to go down. Sorry, as we add ions, the conductivity is going to go down because the precipitate is forming and the precipitate won't have any effect on the conductivity. So as we add stuff, it's going to go down, 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 down. But it's not going to go to zero because something interesting happens. Realize that I can't just add calcium. I can't just add carbonate. The chemical I'm adding is actually sodium carbonate, which is going to be a sodium ion and a carbonate ion. Actually, two of them, two of those. Okay, so far so good? So as the calcium gets used up, the conductivity is going to go down, 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 down. But it can't go down to zero. Why?
Because now the sodium is in it, making it concentrated.
Exactly. The sodium's also in there. So what's going to happen is it's going to go, and it's going to start going back. Actually, it's not going to go up at that angle. It should go up at a lesser angle. Okay? Because once you get to this point, the calcium is gone, and what you're measuring now is just sodium. So you are adding sodium as we go down, which is why the actual graph, we don't look for the absolute value of with the slope of the graph, because that would be way beyond the scope of this course. But you are adding sodium, but you're consuming calcium. That's kind of causing the conductivity to drop. When it gets down to the bottom, your calcium is gone and you're still adding sodium. So this point right here, that volume means the calcium concentration is now 0. And why is that important? Because if I know how much of B I put in, then I know how much A was there. So at the bottom of the titration, this is a pretty typical, that tells me if I know how much moles of B I put in, then I know that equals the moles of A, because it's a 1-to-1 ratio. For every 1 B I add, I used up 1A. It's a 1-to-1 ratio. So if I know the moles of B I added, then I know the moles of A that was present. Cool? All right. And that's what we're going to do. Can I erase this? Right. Maybe I'm going to record this because this is not simple, but it's really important. And we're going to use this idea of titrations a lot. Okay, so you've been given two solutions, 0.5 molar sodium carbonate and 0.5 molar calcium chloride, which you actually are going to use. What volume of these solutions would you mix in order to produce at least 1 gram of calcium carbonate? And that's what we're going to do next week. Maybe even tomorrow. We'll see. Yeah, I'd like to do it tomorrow. So what volume of these solutions would you mix in order to produce at least 1 gram of calcium carbonate? Let me scroll back down to the formula. There we go. Okay. How do we go about solving this? I want to make a gram of calcium carbonate.
Would you I was gonna say, find the limiting reactant, but we're not getting grams.
Okay. Do we ever use grams in a chemical reaction? No. So our first step is we're going to turn our 1 gram, our 1.00 gram of calcium carbonate. We need to figure out how many moles that is. So let's turn that into moles. So go ahead and do that. I love round numbers. And so does the College Board. College Board loves round numbers. So if I'm not mistaken, the molar mass of calcium carbonate is 100.
Yes.
So 100 grams per mole, which means how many moles do we have?
0.01.
0.0100 moles of calcium carbonate. That's just a thing. Which means in a 1-to-1 ratio, if I want to make 0.01 moles of calcium carbonate, I'm going to need 0.01 moles of calcium and 0.01 moles of carbonate. I need 0.01 moles of that, 0.01 moles of that to make 0.01 moles of that. Okay. So then you have the deal about moles. What does moles equal? Your favorite equation, moles equals
Liters times molarity.
molarity times volume, exactly.
Yeah.
So molarity times volume, liters times concentration. So now you know what volume of each solution you should use. Can you calculate that?
Yeah.
What volume you need of this? What do you need of that? And what do you need of that? Because that's what you're doing tomorrow. I hope.
0.005. Oh, volume.
Yeah,
Sorry.
volume. Yeah.
I did.
It's 0.005 liters.
Yeah.
0.001 divided by 0.5.
Oh, divided by some.
0.02.
0.002?
0.02. Just
Yeah, 0.02. Okay. Liters. Is that right? Okay, that's what I was expecting. So 20 milliliters. Yeah. So if our calculations are correct, and they look like they are, then you're going to need 20 milliliters of sodium carbonate with 20 of the sodium carbonate solution and 20 milliliters of the calcium carbonate solution. And when you put them together, they're going to form a precipitate. Make sense? Now I'm tempted to just do have one of you do the titration, one of you do the precipitate, but they're both critical skills. So we're going to do the titration today, and we're going to do the precipitate tomorrow. Okay. And then again, as you add the carbonate to the precipitate, would you expect the fountain to be a rise or fall? We talked about this. You would expect it to fall, and talk about why that is. All right. How are we feeling about this stuff? Good. Okay, cool. So let's talk about what we're doing today. Okay. So I talked about yesterday how to calibrate our drop counter, and as long as our solutions are fairly dilute, the number of drops per milliliter is going to be pretty much the same. So the first thing we need to do is plug everything in, get all the electronics ready to go, and then choose calibrate drop counter, and you're going to open the burette. So if both burettes are vertical, it is fully open. What we usually do is we make one of them on top, adjusted, and one of them fully open. And the reason we do that is if you do it fully open, the drop counter won't work. It's just going to be a stream. So what you want to do is you want to open this one all the way up. And this one's going to be left closed, and slowly open this one until it goes drop, 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 about 2 drops per second. About drop, 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 drop. Okay. Any faster than that, and there's a good chance that you'll get a stream or a dribble, and the drop counter won't work. So you'll have them both closed. You'll fill up the top with your sodium carbonate. Then you open this one wide open, and then slowly open this one till it goes drop, 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 drop. Okay. Then close it again. Okay. Then you're going to get a 10 milliliter graduated cylinder. And you can do the calibration. You can click calibrate, and then this one's going to be like this. And you're going to open this all the way up. It's going to drop, 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 drop until you get about 9 to 10 milliliters. Then you're going to divide the number of drops it gave you by the 9 to 10 milliliters about how many drops you have per milliliter. It's going to be between 20 and 30. Actually, it's going to be between 10 and 30. I think we had a couple that had huge drops. So it's going to be between 10 and 30. And that will be the number of drops per milliliter you're going to use for the rest of the year.
Okay.
Cool? Okay, so do that right now. I'm going to do the calibration part of our rewrite.